Finally, we can get to our hash map or hash table. A short outline: a hash map is a data structure that allows us to set and retrieve key value pairs in constant time or average constant time. It does this using hashes and distributes them over an array of buckets. I've predefined the interface I want to use. These are the functions I want to support. Then let's get to actually implementing the hash map. I'll call the factory method just create map, or let's call it create hash map, hash table, doesn't matter. It takes two generic arguments, one for the key and one for the value, and will return a hash map or a map structure with the key value typing. And to just get the compiler to leave us alone for a second, I'll just convince it that our return type is indeed what do we want to return. We don't need any arguments right now. We could add some like initial capacity or the specific hash and equals functions. I'll for now hardcode them to the ones we have. If the need ever arises, I will generalize this. So let us implement the easiest thing first, the size. We can just store a size variable. We can initialize it to 0 because we'll start off with 0, and we can just return a function here. If I could type, that returns the size value. And before we can write any of the other functions, we kind of need to start with the actual set function. So let's define this next. So set takes in a key and a value, and it does store it somewhere. I just mentioned that we are going to store it in a list of buckets. So let's start off actually defining our buckets, which is just an array. And now we'll need to actually modify our keys and values. I just realized, because we need to make them hashable and equatable. So key needs to extend both hashable and equalable. The value does not need to, but the key has to. Actually, the input here needs to have this typing. Because the first thing we want to do is, of course, compute the hash of our key. That is the hash value we'll use to index into the bucket list. We also want to have a sort of capacity. We'll see later why this is useful. I just start off with a random power of 2. It doesn't need to be a power of 2. I just like to use a power of 2 because we will be halving or quartering and doubling the size of the array, of the bucket array, when we outgrow the actual capacity. And powers of 2 are very nice here because we never get weird floating points. We have computed our hash, but we also want to throw the mod on this of our capacity. And this is the index into our bucket. So our bucket is the bucket of our hash, our index, but essentially. And if our hash happens to be undefined, now the question is, do we want this to ever be undefined? And we should give this actually a typing. and that is value pair equals key value. This is an array of key value pairs. Actually, an array of that. Let's add some helper types. I just mentioned we'll have a bucket, which is an array of our key value pairs, and our buckets is a list of buckets, and our buckets is a list of buckets. So our bucket is now either a bucket or undefined. The question is, can it ever be undefined? I would say we can always force our buckets to actually be the right size. So let's actually do that. And give it the size of our capacity. And let's fill it with the empty arrays. At this point, our bucket can not be undefined anymore, so we can tell TypeScript this is always defined. Next, we want to see if our key is already present in the bucket. So we can check that by just running a aggregate over it. In this case, I'll use the sum function, so const key is present equals bucket sum. And then I will call the equals of the other and the key. And let me just quickly get rid of all the error lines, because they're starting to be kind of in the way. And this is not actually other, this is just the key of our key value pair. I need to do that over here. Okay. So if our key is present, we want to replace that entry. And if our key is not present, so if our key is not present, let's check that first. Then we just add to the bucket with a push to the end our new key value pair. Otherwise, we want to replace it. So instead of the sum, let's use the index of instead. And this will not work because the index of doesn't take a function. Let's find it instead. And if our key is present, or this is actually our key value pair, if our pair is present, then we can replace the value with our new value. Right. To do, potentially resize. Resize the map. How we do that, we'll cover then. This not null assertion, this undefined assertion is intentional. We know that the capacity of this array should always, that the array size here is always the capacity, and it's always going to be filled with our values. So when we take the mod here, it is not possible for us to be outside of the range. Now, the get looks very similar to this. It's essentially the exact same thing, except that if we find the pair, we just return the sum of the value. And if we do not find the pair, then we return none. Like so. At this point, we could consider extracting these pieces of code here, because we found them multiple times now. And the unset does something very similar. It again finds the same bucket and hash. But instead of doing anything else, it'll create a new bucket. By filtering over the old bucket. And we'll keep everything that is not equal to our key. So we can take our key here again and call our equals again with a key in the bucket and our key that we provided. And if it's not in the array, we keep it. And then we set our buckets, override the bucket we have of the hash with the new bucket. And I, for some reason, said this returns a maybe. I think it's fine if this returns also nothing. And we can simply return nothing at this point. We do not return this. And we also need to potentially resize at this point. Let's quickly do a sanity check if any of this makes sense. And again, output this. So we would expect the first call to not match anything, which it doesn't. It doesn't have a just, so it turned into the none. The second call found the value we had, and the third call found none again. So our set and map get seem to work. This is obviously not good, rigorous testing, but it does give us an intuition if it does work at all. Now, what happens when we put more than 32 values in here? So the base assumption on how this works is that the hash function is good, and it'll distribute our keys more or less evenly across this array. But if a key has the same hash value than another key, they'll add it to a list. But on average, these lists are going to be length 1. And that gives us average access time. Of course, this does not hold true once we once we break our capacity here. And we need to decide to do something when we are too full to get more space. And also, we don't want to just waste space, because of course we could set this to a large value. So we want also to shrink the map when we are like just too small at some point of time. The load of a map is usually what it's. We can measure under how much load the map is by just computing a value of the current size divided by the capacity. That it tells us how full it is, and in my case, I will be shrinking the array if we drop below 1/4 size, below 1/4 load. And I'll double it once we reach load of 1. The reason I've chosen these values is because it makes the math very simple, and the average runtime will be constant in that case, even with the resizing. Because if we really think about it, every time we add an element, this is constant if we assume that it's well distributed. But once we've added capacity many items, we'll spend capacity many time increasing the size of our array, because we'll have to copy over our elements. Meaning we spend for every element that is in our hash map now 2 times constant time. The same argument is applied for shrinking. And the reason I'm picking 1/4 and 1 is that when we halve the size of the array, when we hit 1/4, then we'll put the map back into the middle. So we won't be constantly crossing the threshold up and down, up and down. Like if I'd pick 1/2, for example, and if we double it, then obviously if we remove an element, now again, we'd drop below the 1/2 threshold again, so we'd need to shrink again. So that's why my cutoffs are this way. There are better or different load factors to use, but it doesn't mean but when we're not doubling or halving the size of the array, we are doing other sizing, and it makes the math a bit uglier. And this is more a exploration of the concept than an implementation of a high-performance map. If I wanted to do a high-performance map, I'd be abusing the underlying JavaScript maps, probably to do the hashing for me, or at least to keep the buckets. Then I wouldn't need to do any resizing it, because it would already have the resizing implemented in it. So we can compute the load, I just said, as size over capacity. We can define a constant of min load. And let's call that 1/4. We have a value of max load, which is 1. We'll also have a constant of min capacity, because we don't ever want to shrink to size 0, for example. At some point of time, we can just say, yeah, whatever. And that's what I'm gonna pick with 32 here. This can then be min capacity. We can compute our load. We know our current capacity. And let's add a resizing function. What does this function do? Well, it needs to check our load. So if our load is smaller than the min load, then we need to expand. If our load is larger than the max load, then we need to expand, and we need to shrink here. And else we just don't do anything. How does this work? Well, the hash value is dependent on the mod, so we can't just copy over the items. They will have new slots to go into, new buckets to be assigned to. So we'll need to redo that. First, let's recompute our capacity. And I said I will halve it. I should not mix those. And our new capacity is going to be our old capacity divided by 2, or the absolute min capacity. Which we don't want to fall under. We can do the same thing here. We don't need to do the max because we're only increasing and we don't have a max capacity. And in this case, we are doubling our capacity. Let's declare new capacity up here. And assign them, because the code that actually does the resizing would be identical for both of them, just the capacity computation is different from them. And if the new capacity is not the same as the old capacity, so we are actually doing resizing, then we do something. We can set our capacity equals to new capacity. We don't care for the old capacity anymore. Capacity is a LUT now. We can store our buckets, our old buckets are just our buckets, and we can create our new bucket list the same way we created it before, a new array of capacity, and we fill it with the empty values. I just noticed we never increased size. We should do that. So let's quickly fix this. When we do push, we also add to size. And when we unset and we found something, so we need to know if this bucket has a different size, essentially. So if new bucket dot length unequals bucket dot length, then we know we actually removed a value. It says type number undefined is not assignable to number. For some reason it claims new capacity could be undefined. And that is because we should just set it by default to the capacity value. We overwrite it in the case we are either over or under. We set our new capacity, we set our new buckets to our new capacity, and now we need to transfer all items from the old buckets to the new ones. So we could just use the set, except it changes the size here. We can create an internal helper function, which this set can use, which I'd like to do now then. Which also takes a key and a value, and it returns a Boolean. It'll just tell us it worked or not. Like, as in this Boolean says, we overwrote a value. It's gonna be false if we overwrote a value, and it's going to be true if we actually inserted a value. So we can then take this entire code here. We can put it into our set. And instead of increasing size here, we'll return true. Otherwise, we'll return false. At this point, we don't actually need this if else here. We can just do this because we're returning. And now here, all we need to do is call the internal set. And increase the size. If we actually insert it. We can also then call the resize function, because we actually changed our size. And at this point, we can then iterate through our old buckets. For each here, this is a bucket. And then for each bucket, we can also go for each, and this is each actual entry pair in this map. And then we can call the internal set of this key value, which does not actually change our size. And we don't care if we insert it or not. Actually, everyone here should insert, because otherwise we have a critical error. Let's make this slightly more readable. And we'll call resize in this case as well. I think we're done. I'm just double checking. I'll just add an expansion factor, and I call it 2, and I call a contraction factor. (0.5). That is in case I ever want to use different values here. I can control it via these parameters. We could, in theory, also expose them as settings, I guess, in the creator here. And instead of just multiplying it here, we'll just use the expansion factor. And instead of dividing, we'll take a multiplication with the contraction factor. Now it'd be interesting to see if our map actually works. So let's set our min capacity to 2 for now. And add a helper function just for a bit, which will print out. Maybe we'll actually wanna keep this string or print or something. Let's call it to string. Let's just call it to string, which will return a string. Now something's interesting happening here. And I don't know why. They all appear to be in the same bucket. I see. The fill is not working as expected. This here, it's probably the same. Everything is the same bucket here. So this should be a we want to actually create a new bucket per statement here. And the same thing when we create it down here. And if we look at it now it makes a lot more sense. We see we actually have a hash collision here. But otherwise we see that it is actually fairly well distributed. Next time we'll add the set, and then I'll return to actually doing something more interesting than implementing these data structures. It's just I want a map and a set to work with. If you've got any questions, feel free to leave a comment or join my Discord. And otherwise, see you around.